Hi everybody, today's chemistry lesson is on the history of the atom. So I want us to be able to answer this question: how have we come to understand the structure of an atom? If I asked you to right now draw an atom on your paper, I'm guessing you would draw something like this, with a nucleus and protons and neutrons and electrons and maybe even orbitals around the nucleus. So how did we get to the point of understanding this? A long time ago, back like Greek times, there was a man, Democritus, who came up with the word atoms. Atomos was really the name he came up with. And he believed that everything was composed of a certain structure, and that if you had iron atoms. And if you had zinc, you had zinc atoms, and if you had helium, you had helium atoms. But we didn't really understand anything at that point about what the atom structure was. So how did we get to the point that we understand all of this? So as we go along, I want you to add this to your notes. Each one of the scientists that I tell you about, I want you to add the information, and then I want you to leave at least 10 lines so that during class, if we want to add more diagrams or more information or something else that is going to help you remember it better, you have some room for it. So we're going to start off with a man named John Dalton, and he was from England, and he came up with what's called the cannonball model. And this is in the early 1800s, and basically it's saying that atoms are indivisible, meaning you cannot divide them up in any way. So we know that's not true. Each one of these scientists, we sort of figure out that part of their belief worked and part of it might not necessarily be true. The same thing might happen of our current model. We might realize that some things might not be true. But he did lead us to this really important thing called conservation of mass. So I have a little drawing to explain conservation of mass, and this is a reaction. So here in my reaction, I want you to draw this reaction too. So I have this one molecule that is a compound. There is one of this atom combined with two of these white atoms. And then I have another. This is not a compound, it is only an element because the two atoms are of the same type. And after my reaction, I still have just one of these large atoms. I have two of these medium-sized atoms, and I have two of the small atoms. They are arranged in a different way, but everything has been conserved or saved. Nothing was created, lost, destroyed, or missing. So that's a really important thing. We're going to follow that all the way through the year. Conservation of mass, conservation of charge, conservation of energy. All right, our next scientist, J.J. Thompson. So J.J. Thompson, just about 100 years later, was working with what they call a cathode ray, similar to what used to be in televisions. And he found the first subatomic particle, which was an electron. The way that he figured this out was that he had a gas going through a cathode ray tube. And as the gas went through, particles were emitted from it, and the particles bent towards the positive. And he figured out, gosh, where are these particles coming from? They have to be coming from the atoms of the gas. So gas atoms must actually have subatomic particles. And since they bent towards the positive, they were negative themselves. So he found the first electrons. His model is called the plum pudding model. And back in that time, plum pudding, if you can picture like chocolate pudding, but throw something in it, like raisins or something like that. Plum pudding is more like a bread with little fruits in it. But if you picture, dirt. You know how you order dirt at a restaurant, like maybe when you're a kid? And it would be chocolate pudding, and inside it there would be gummy worms and Oreo pieces and marshmallows and stuff like that. All of those particles inside are the negatives, and then the chocolate pudding is the sea of positive. So that's what he believed an atom looked like. So I'm going to show you a couple pictures here. First of all, this is a cathode ray tube, and in class I'm going to show you how that works. And then here is an atom that is that first model of the plum pudding, where you could see the first subatomic particle, the electrons, and they're negative, and then it was just a sea of positive. No positive particles, just a sea of positive. So again, we know his model is not totally right, but we're getting closer and closer to more information about how an atom is divided. All right, next thing, our next scientist, Ernest Rutherford. So Ernest, this is now in 1908, so just like 10 years after our last guy, he found the nucleus, and I really, really love his experiment. I'm going to act it out in class for you guys. He fired alpha particles. So alpha particles have a mass of 4, and they have 2 protons. So basically it's a helium nucleus, and it's positive. And he would fire them at gold foil. So gold atoms, very thin, spread out, makes gold foil, just like aluminum foil, aluminum spread out thin. So gold foil, and he would fire these alpha particles, and he expected them to all go through. Because if they all go through, it's proving that sea of positive with tiny little electrons. And electrons aren't anything dense enough to cause anything to happen but to go right through. But some of them deflected. So the deflections helped prove 2 things. First of all, it proved that there's a nucleus. Something small, because it didn't hit it very often. Something dense, because when it hit it, it bounced back and deflected, and something positive. The alpha particles are positive, and if it was negative, they would have been attracted to it, but instead they deflected. So we proved that not only was there a nucleus, but the nucleus must be small, dense, and positive. Then the other thing that it proved was, since most of the particles of alpha particles went right through the gold foil, most of an atom is actually empty space. And I've shown you before how if the whole smartboard is an atom and I draw just a tiny little dot, that one little dot would be the nucleus. So it's proving most of that atom is just empty space. So we call his model the nuclear model. And there it is, just this circle, the positive small dense nucleus with those little negative electrons that were found from Thompson before. So each scientist just tweaked it according to what his experiment figured out. All right, I have this next diagram because I really like it for explaining Rutherford's experiment. If this is an atom of gold, he expected, according to the plum pudding model, that all of the alpha particles will go right through. What happened is most of them went through, like these yellow arrows that go through show, but a couple of them hit and deflected. Hit and deflected. So if they deflect, it's proving that there is something present. It just didn't hit it very often, so it must be very small, dense, and because it's not attracted to it, it must be positive like the alpha particle. So I thought this was a great representation of the change from plum pudding to now a nuclear model. All right, our next guy, oops, wrong screen. All right. Here we go, Niels Bohr. So here's our next scientist, just a couple years after, 1913. He figured out that electrons have specific energy levels, and I call them Bohr rings. So the rings that go around the nucleus, sometimes we call them energy levels, sometimes we call them orbitals. Bohr was the guy that figured out that there actually is an amount of energy that is pretty set and specific for an electron based on where that electron is. Which energy level is it on will determine how much energy it has. So we call this the planetary model because it looks like rings. Again, I call them Bohr rings. I don't like to draw the Bohr rings because it's a lot of work, but the planetary model is a good description because you can imagine the rings around it. So here is a nice diagram where you see the nucleus with the protons and the neutrons, and along the way there are some scientists that figured out the presence of neutrons. And then here we have orbitals or energy levels or rings or shells where you find the electrons. And the ones that are close to the nucleus are low energy, and the ones that are further from the nucleus, the electrons have higher energy. And I like to think of this as if you have your positive mama nucleus in the middle and the electrons are the kids, when the kids are close to positive mama nucleus, they're well behaved and low energy and nice and calm little perfect angels for mom. But as the electrons move further from mom or further from home, they tend to have higher energy, and the further out you get, the more energy they will have. All right. Next one. This is our last slide for today. So there's really too many scientists to name, and there is not a model named after one scientist because so many people have worked together to get our current thinking about what an atom looks like. So we have two names for it. The first is the electron cloud model. And this is showing, electrons are not as perfectly set on rings as Bohr believed. Instead, they behave more like waves, and they're in areas where you consider them most probable locations. So the orbitals still exist, but they're not perfect. And the next little line here tells you they behave more like waves in their movements than perfectly circular orbitals. So that is why we have the electron cloud or the wave mechanical model. And the picture, it seems like we're going backwards with our picture, but the picture actually is like some dots in the middle that show the protons and the neutrons, and then lots of dots outside of it, and that is the areas where you are most likely to find an electron. So if you have questions, make sure you ask me during class. We're going to be doing all sorts of activities to make sure that you understand this progression of events and what each of the major significant experiments were and what that led us to believe. Thank you.